Hello everyone, welcome to my programming club. Today we will be solving another Leetcode weekly contest, and the contest number is 357. Now let's begin with the first problem of the contest. The first problem's name is faulty keyboard. So the problem statement goes like this. You are given a laptop whose keyboard is faulty whenever you press character I. What it does is it reverses the string that you have typed so far, and typing other characters are working as expected. So you have to return the final string that will be displayed on your laptop string. If you give a input of string, for example, let's say the input was string. So what you will do is you will check character by character. You will be forming string character by character from left to right direction. In this direction you will be forming the string, and what you will do is first you will check for the first character, which is S. Now you can append it in the final string. Let's call the final string the result, and then you check the second character, it is T. You can append it. Then the third one is R. Now the fourth one is I. Since I reverses the string currently formed, so the reverse string will be R T S, and I will not be appended. It only reverses the string. So the fifth character is N. N will be appended, and then G will be appended. This is the uh, you can see output of the given input, sample input. So this is how we have to do. So let's look at the constraints. Constraints are pretty low here. So even if you give a n square solution, it will be accepted. Even a n square solution will be accepted since 10 raised to power 8 operations are allowed. In 1 second. So the number of operations that your program will do should be lesser than these number of operations. Then you will not get a TLE. So here n here is at max 100. And if we square it, you will get 10 raised to power 4, which is lesser than 10 raised to power 8. So those of you who are not familiar with this concept, how the time complexity of accepted solution varies according to input size, then I will provide a link of article describing this, and you can check that article out, and then you will be able to understand what I have just told you here. So it will be accepted, our solution will be accepted. So we'll do what the problem statement says. So we will just form a simulation of the process of making the string according to statement. So what we have done is we have initialized the result variable. Initially the string is empty. We are traversing from left to right. So and we are building our string. If the current character happens to be I, what you will do is you will reverse the string, and if the current character is not I, in another case you will append the character to the string, and at last you will return the string. So this wraps up the first problem of the contest. Now let's move to the second problem of the contest. So the second problem name is check if it is possible to split an array. So what you are given is you are given a nums array of length n. Any integer m is given to you. It is the nums array. It is of length n, and integer m will be given to you. You will need to determine if it is possible to split the array into n non-empty arrays before after performing a series of steps. So what you have to do is, let's say this array was given to you and m was given to be 4 here. So you are required to tell whether you can split the array in these segments. These are separate segments, which is equal to the number of these segments will be equal to the size of the array. So you have to basically separate out each element in the array. And what are the rules according to which you will be doing so? These are the rules. So if you, let's say, decide to split a subarray, let's say let's subarray is a array, subarray. It is also given to you. A subarray is a contiguous non-empty sequence of elements with the array. So what is saying is the subarray cannot be, for example, the array is 2 3 1. The subarray cannot be this, since the sequence is not contiguous. 3 is missing here, 3 is not present, so this is not contiguous. It can be 2 3, since the 2 3 it is a sub part of this whole array, and they are contiguous, so it is a subarray, and the whole array is also a subarray of itself. So I hope you are clear with what a subarray is. So in each step you can select an existing array which may be the result of previous steps. So if you have performed some previous operations on an array, you may select an array. What you will do is, if you will perform a split, if after split, let's say you perform a split here, for each of the resulting subarray, what will be the two subarrays found? This will be the one subarray that will be found, and this will be the another subarray that will be found. So after split, each of these subarrays should satisfy either of these two conditions, which is either the length of the subarray is 1, either length of subarray should be equal to 1, or what will be the other condition. The other criteria can be is greater than the sum of the subarray is greater than equal to m. So what will the sum of this subarray? Sum of this subarray will be 4. So it is equal to m. So what will be the other criteria? Sum of subarray greater than equal to m. So this split that was done here satisfies these two criteria. For each subarray, the subarray satisfy the criteria from either of these. So it is a valid split. So you can perform this split. So after performing such valid splits, any number of such splits, you have to tell whether you can split this array into uh, segments where the number of segments is nothing but equal to the length of the given array. So you have to separate each element out. Two will be separate, these two will be separate, and this one will be separate. In this example, for example, uh, 2 will be a other segment, 3 will be other segment, and 1 will be other segment. So each element will be separated out from the whole array. So you have to tell whether it's possible or not. So how we will be solving it? Now let's look at the constraints part. The constraints are here also pretty low. The length of the subarray given is of order 10 raised to power 2, and the value of the numbers in the array given is also order of 10 raised to power 2, and the m is given of the order 200. So what we will do is, if let's say for example, I have given you one sub array which is containing only one element whose size is 1. So you can return true here. Why we are returning true? Because one condition is satisfied here. uh, the length of the subarray is 1, and also the number of the number of subarrays formed after splitting is equal to the size of the given array. So n is equal to number of subarrays formed, or say number of elements separated from the given array. So it's a valid split, and we may return to. Same goes for the uh, case when the size of the given array will be 2. Here the size is 2. So we can perform this split, and each of the subarrays formed is having length 1. So at least one condition is satisfied here. This condition is satisfied. So the case will also be returning true. So in these two cases, what you will do is you will simply return true, since the conditions are being satisfied. And the trickier part is now how will be the condition satisfying. If you look at this example, this sample input, yeah, let's look at this input. M here is given to be 6. M is equal to 6. So it can be easily proved if there are two adjacent elements whose sum is greater than or equal to m, then answer will also be true. Always be true. True always. So how we will be checking this? For example, let's say here these are the two elements whose sum is greater than equal to m. So in this case it is equal to m. So what you will do is, let's say you take a complete array and you separate this part out, 3 3 2 3, and this is the two parts that you separated. So this is another part, this is another part. Its length is 1. One criteria is being satisfied, and sum of this is greater than m. So the another criteria is also satisfied, so it's a valid split. Now you will check for another this part only, since it is of length 1 only, so you will not be further splitting it. Now you will check for this part. Okay, what you will do is, let's say you perform a split here. It's of length 1, and sum of these is also greater than or equal to m. So this is also a valid split. Now you will consider this part, since it's of length 1, it will not be considered further. So the array is like this now. So you can perform a split here. Length is 1. The sum is uh, equal to m. So you can perform a split. Now this will be not further considered. This 2 will be further considered. Now you can perform a split here, since both are having length 1. So at least one criteria is satisfied. So yeah, you can separate out each element in the array. So you will return true. So this will be the sufficient condition to check if two adjacent elements are having sum greater than or equal to m, then you will return true, otherwise false. So this wraps up the second problem of the contest. Now let's move to the fourth problem of the contest. And the sorry, not fourth, the third problem of the contest. And the third problem is find the safest path in the grid. So what you are given a zero index 2D matrix representing a grid of size n cross n. Each cell is either containing 0 or 1. 1 indicates that at cell at with value 1 there is a thief present here, and 0 indicates that thief is not present here. So initially you are placed at the 0 comma 0 index, which is this block. Let me quickly copy this image. Yeah, you are initially placed here, and you have to go here. You are initially placed at 0 comma 0 since it is at 0 based indexing. Grid is having 0 based indexing, and the size of grid is n cross n. So the number of columns and rows are equal, and you have to reach n minus 1 comma n minus 1, the last cell. You are at the first cell from the top, and you have to reach the last cell from the bottom. Last cell at the bottom. So what you have to do is you have to consider the path that you will be taking. Let's say you follow this path. Uh, there is a number associated with each path that you will follow. It is called safeness factor. What safeness factor is? Safeness factor is defined as the minimum Manhattan distance from any cell to the path of any cell in the path to any thief in the grid. So, if we consider this path, this cell is having zero distance from the thief. Thief is present in this cell. Now this says, what is the Manhattan distance? You may ask. Manhattan distance is nothing but, let's say x and y are the coordinates of the cell that you are at, and your thief is present at a comma b. Then what will the Manhattan distance of cell to thief cell? It will be nothing but absolute difference of the x coordinate plus the absolute difference of y coordinate, y minus b. This is what the Manhattan distance is. Manhattan distance. Sorry if the spelling is incorrect. I hope this does not affect your understanding of the solution. Manhattan distance. So this is what Manhattan distance is. So it is having distance 0. Now this one is having distance, minimum distance 1 and 2. So this is having distance 2. Now you went to this path, this cell also. It is having minimum distance 1, since only one cell, it's only one cell far away from the thief that is nearest to this cell. Now it's this cell's distance from the nearest thief cell is 1. The thief is present directly below it, and it's this cell's distance from the thief cell is 0, since it is itself a thief cell. So these are the distances. Now for this particular path being followed, if it's being followed, what is the minimum distance from the nearest thief cell among all the cells visited while traversing this path? it is 0. So for this particular path, the safeness factor will be, let's call this SF, it will be 0. So I hope you are able to understand what the safeness factor is. So what you have to do is you have to return the maximum safeness factor possible among all the paths that will lead you from uh, this cell to this cell. So among all the paths that you will be following from 0, 0 to n minus 1, n minus 1, you have to return the path with the maximum safeness factor. Maximum safeness factor path you have to return. What is the value? What will be the value of the maximum safeness factor of the path that are leading from 0, 0 to n minus 1, n minus 1 this cell. So you have to return the maximum safeness factor. So let's look at the constraint part. The grid length is given of the order. Let me quickly change the slide. The grid length is n is the grid length. It is also equal to the grid breadth, since it's n cross n grid. So n is here given of order 400. So and grid is, each value in grid is either 0 or 1. And this is what I have told you before. This is what I have told you before. And there is at least one thief in the grid. So at least one thief in the grid. At least one thief cell present. So these are the constraints. Now, what will be the brute force way to solve this problem? What you will do is you will check all the paths, and while checking all the paths, you will check all paths from 0, 0 to n minus 1, n minus 1. So, and what you will be doing is you will be calculating their safeness factor. Now let's say for a moment that I have given you a grid representing, let's call this distance grid, DG, distance grid. The value of each cell represent nothing but the distance, Manhattan distance, this cell to the nearest sheep cell. So you are given a grid representing the, where each cell's value represent this entity. So if I give you these values, would you be able to calculate all the path with the maximum safeness factor? A total number of cells that are in the grid are n cross n, and for each cell you will be having 4 options. Since you are allowed to move in the adjacent cells, let's say you are currently at this cell, then what will be the adjacent cells to this cell? These will be the adjacent cells, these 4. So for each cell you will be exploring 4 options. You can go in 4 directions for each cell, and the number of cells are n cross n. So 4 into 4 into so on. How many number of times? N cross n number of times. So 4 raised to power 400 square. This is very much greater than 10 raised to power 8. So you will, what the 10 raised to power 8 is representing the number of operations in 1 second. So those of you who are not familiar with how the time complexity of the accepted solution varies with the input size, I will provide a link for article describing this. Right now, what I can tell you is in 1 second, these many number of operations are allowed. And if your program is reaching equal to or greater than these number of operations in your program is reaching equal to or greater than these number of operations, then you will get a TLE and your solution will not be accepted. So how we will be optimizing this brute force approach? We have to optimize it. First of all, what we will do is we will form this DG grid. Each cell in DG grid is containing a value which represents the distance of that particular cell to the nearest heap cell. So I hope you are able to understand what I am saying. For example, let's take an example here. Now let's print the value of the DG for one sample input. This is one cell. This is one DG grid. What it's for? Let me quickly copy it first. Yeah, this is a DG grid, and what is the input? Input is nothing but this. Input is this grid, and I have generated a DG grid, distance grid, DG distance grid, which represents now this cell 0, 0 is at zero distance from the nearest heap cell. This cell is at distance. Now, what distance is considered? Distance is Manhattan distance. So this particular cell here is having 2 units of distance from the nearest heap cell, which is 1 and 2. You can go from here to here, these 2 units. So this is what the distance grid is representing. We will be forming this grid. Now, how we will be forming this grid? Let's say you are present currently at this cell. This cell you are at. Okay. Now, how you will be arriving at this cell? You can either be arriving from this direction, or sorry to the direction. You can either be arriving from this cell or this cell, or you can be arriving from this cell, or you can be arriving from this cell. Now, what we have done is we have considered these two cases separately. We have filled our this distance grid in this direction. It will be from top to bottom. This top to bottom way of filling will cover these two directions, these two. Now what we have done for these two directions is, these two directions, we are filling our distance grid from bottom to top. And these two directions will be covered. So what we are essentially doing is, once we have filled from top to bottom, when we will be filling from bottom to top, we will be checking if the distance of current distance of a particular cell is lesser than what is being calculated from this bottom to top approach. Then we will not change it, and lesser or equal, then we will not change it. And if the distance happens to be greater than what bottom to top approach is telling us, then we will change the value of this dg grid. So dg grid will be populated via two traversals. One will be from top to bottom and one will be from bottom to top. So let's quickly move to the coding part to see how we are filling this dg grid. This is the from top to bottom filling of dg grid. Initially, you are placed at 0 in this top to bottom strategy. We are starting from this index, this cell, and from bottom to top one, we are starting from this cell. So I hope I am clear. So if the starting point is having a 0, is having a thief, if the starting point of the top to bottom approach, top to bottom filling is having a thief, then you will mark the distance of the cell to from thief to 0. Then you will be filling the grid in top to bottom fashion. If you are at currently 0, 0th cell, you have already checked for that and already filled that. And what you will be doing is you will be considering all the values when this grid will be formed. Initially all the values will be having maximum integer value, maximum integer value possible, and so on. We are assuming that each cell is at maximum distance from the cell. So initially all the values are maximum integer value possible. So initially we have filled all the cells with maximum value possible. Initially we are considering each cell at max in distance, integer distance possible away from the nearest thief. Then as we discover the thieves in the grid, we will be updating this distance. We will be taking the minimum distance. So from which two directions your thief can be approaching you? If you are following this top to bottom approach, it can either approach you from a cell above you. If you are at this cell, it can either approach from the cell above you or the cell from left hand side of your cell. So these two will be considered. And you may ask that what is this r is greater than 0 is 4. These are nothing but to check if we are currently not violating the boundaries of the board. Otherwise, you will go outside the boundaries of the board. So you will be checking these two conditions. For present cell, if can come from top cell, which will be nothing but this r minus 1, or left cell, which will be nothing but this c minus 1. So you will be taking minimum of this. If the minimum value happens to be maximum value possible for integer, you will not be updating the distance grid for that particular cell. Means this cell is not reachable by any thief. So it will and the max value will stay maximum. In case that's not the case, you will be updating the value with the minimum distance possible from these two cells plus 1, because moving from these two cells, this cell and this cell to this cell, will take 1 unit of distance. So you will add 1 to the minimum distance you have achieved here, and this is how you will be filling. And similar approach you will be taking up for the down to up or bottom to top approach of filling the distance grid, and at last you will be having the final distance grid. Now you may ask, if now we are having the final distance grid in which each value is representing the closest distance of that cell from the thief cell. How you will be forming the solution, you may ask. What we will do is we will consider a binary search for the possible maximum SF possible, max SF possible. Is safety, what was the name of this factor? Safeness factor, yeah. This maximum safeness factor possible will essentially lie between 0 to, or let's say maximum integer value, or let's say take 10 raised to power 9. This will be lying between this value, and what you will be doing is you will be, now you know that you have to go from this source which is 0 comma 0 to this destination n minus 1 comma n minus 1. So in these cases, instead of our depth first search DFS, BFS is more suited one. When you know the source and the destination, and you have to arrive there at the minimum time possible. So you have to, what you will do is, if the source and destination is known to you, PFS will be a more suited approach. Now you will be generating a test safeness factor. It will be the maximum value of the safeness factor that will be possible. So you will be doing a BFS and checking if this test safeness factor satisfies the condition. Which are the conditions I am talking about? Condition will be that uh, for the for the minimum distance of any cell in, let's say, this P1 path taken from source to destination, the minimum uh, distance of any cell should be greater than this test, should be greater than this or equal to this test safeness factor. It will be the safeness factor for this path if all the values are greater than or equal to this safeness factor. Then for this particular path, the safeness factor will be this test safeness factor, and it will be possible to take this safeness factor. So you may ask, what If the safeness factor is not satisfying, what we will do? What we will do is, let's say the test safeness factor was lying here. We will reduce our search space to half, and we will search in this range. Now, the TLE that was we were getting from the brute force approach will be removed, since for BFS you will be checking at most 10% cells, which is of order 400 into 400, which is 16000. It is of order 10 raised to power 5. So, and this whole range, if you apply BFS over this whole range from 0 to 10 raised to power 9, basically I have taken a sufficient number, uh, which the safeness factor will be, below which the safeness factor will be maximum safeness factor. So I have taken a large enough number so that the safeness factor should be in this range 0 to 10 raised to power 9. So if you apply BFS over this range, it will take you log of 10 raised to power 9 operations, and multiplying by these number of operations, your time complexity will be of order 10 raised to power 5 into log of 10 raised to power 9. And these number of operations are lesser than 10 raised to power 8 operations allowed. So your solution will be accepted. So now let's move to the coding part to see how we are applying binary search for the maximum safeness factor possible among all the possible paths. What we have done is, we have initially generated the distance grid, by following these two approaches from top to bottom. Let me quickly zoom out so that you will be able to see the code in a clearer way. You have What you have done is, first you are making the, or say generating the DG grid whose each cell value represent the minimum distance of that cell from the, or to the nearest sheaf cell. So this is what you are checking for. So if you are checking for, if you are having, once you have generated this distance grid by filling it from two directions, top to bottom, and what was the other direction? Bottom to top, down to up, and you will be having the distance grid generated. Then you will apply binary search with DFS. It's nothing but binary search. If the value is the value of safeness factor that we are currently generated with binary search, to check that value generated is satisfying the condition of valid safeness factor, we are simply using BFS. So this is essentially binary search only. So what we have done is, we have considered the range big enough to accommodate possible maximum possible safeness factor. Let's call it SF. So I have taken the range large enough, and then what you are doing is you are essentially applying binary search. This is nothing but a standard binary search. But you are generating the mid value of the present range and calling this mid value as test safeness factor. We will be testing this. Is this safeness factor is the test safeness factor is a valid safeness factor for all the paths possible. For the path possible which will be having maximum distance, maximum safeness factor. For the path which will be having maximum safeness factor. So for testing whether the safeness factor is a valid one or not, we are using BFS, breadth first search. Those of you who are new to BFS I will be providing a link or article describing what BFS is. So what we are doing is we are checking, we are starting from the, what we are doing is starting from 0, 0 cell and checking for the path with max stiffness factor. Each cell in that path is having distance to nearest heap greater than or equal to test safeness factor. So if it's not the case, if you are initially situated at 0, 0 and it's not the case, you will simply return false. This safeness test safeness factor is not a valid one. If that's not the case, you will proceed further. And what you will be doing is for each cell, you will be having 4 directions to go. For each cell, you will be having 4 possible directions, and you have to avoid looping condition. What the looping condition is? What the looping condition is? For example, let's say you are at this cell. Now you went like this and then came back to this cell. Since you are allowed to go in 4 directions, you will be keep on spinning in this loop. So and it will be infinite. So to avoid this looping condition, we will be taking a 2D array or say vector. Array is in Java and vector is in C++. In C++, array is also there, but generally we take vector. So you will be taking a 2D array and you will be marking the indices that you have visited in your path, that you have gone through, the cells that you have gone through in the path earlier as visited, so that if you encounter these cells again, you will not be visiting them, so that you know that you have already came from this way, so that you will not follow that way again and again. So this visited array or say vector is to while looping condition. Now from 0 comma 0 to for each cell you will be checking all the four possible directions, and if you are neither encountering a loop, if you are neither in a loop or nor going outside the boundaries of grid, then the option that will be considered from the current cell is having four options, either to go in this up direction, left, right, or down. Now let's say you are considering this option. If this option is neither making us to enter in a loop, nor it's making us to go outside the boundaries of the grid, then this is a valid option. We will enqueue it in the queue. We will add it into our queue of the standard queue that we used in BFS approach. I highly recommend you, if you are new to BFS, then to check out the link of the article that I will be providing what BFS is, that will be describing what BFS is, and then come back here. So what we will be doing is for all the four possible configurations, we will be adding only the valid ones. And to check if the coordinate is a valid one, we have made this function. This function ensures that we are not neither entering a loop nor we are going outside the boundaries, nor we are going outside the boundaries of the grid. So we will be enqueuing that those values, and we will be marking them as visited, so that we would not be looping in this path again and again. And as soon as we hit the last cell, we will return to. As soon as we hit last cell, we return to. And for a cell to be a valid one, it it is mandatory that its distance from the nearest thief is greater than the stiffness factor. Distance from nearest thief cell is greater than or equal to test stiffness factor. So if that's the case, and that's not the case, we will skipping that coordinate and checking for other coordinates. So that's pretty much it. If this value returns true, means this safeness factor is sufficient, is a valid one. Then you will be checking for a safeness factor greater than this safeness factor, and your range value will be reduced to half. And this is a standard binary search. At last, you will be returning the maximum safeness factor possible. So this wraps up the third problem of the contest. Now let's move to the fourth and the final problem of the contest. And the problem's name is maximum elegance of a k-length subsequence. So the problem statement goes like this. Initially, you are given a 2D integer array of items where each uh, element in that array is a array itself, and what that array is having one index is having the profit that item will be providing us, and other is indicating the category of that item. So you have to what you have to do is you have to find the subsequence with maximum elegance possible among the subsequences of this 2D integer array possible. So this 2D integer array is representing nothing but the elements, and for each element it's the profit associated with that element and the category of that element is given. You have to find a subsequence which is having maximum elegance. Now what is elegance? Elegance is defined as the total profit the subsequence is providing you plus square of number of distinct categories in that subsequence. For example, let's consider this input. Now if we were to find what is the maximum elegance possible, also there is a one constraint that is to be followed. The length of the subsequence length cannot exceed, it should be lesser, it should be exactly equal to k. Neither it can be less than k, or neither it can nor it can be greater than k. It has to be equal to k, and k is given here to be 2. So how we will be checking this? Now let's say I consider this as a subsequence. This is a subsequence of length k, of 2 length. What will be the total profit? 3 plus 5. And what will the elegance of this subsequence we have selected? It will be total profit provided by the items in the subsequence plus number of distinct categories of items. There are two distinct categories, category 1 and 2, plus 2 square. So this will be the elegance of this particular subsequence. And then those of you who are new to what a subsequence is nothing but a sequence that will be generated after deleting 0 or no elements in a given sequence. Let's say this is a given sequence, and what will be a valid subsequence be? 1 3 4 5 will be a valid subsequence. Also 1 2 3 4 5 is also a valid one. You have not deleted any of the number in the given sequence. This is the given sequence, and provided that the order in which these elements are appearing in the given subsequence given sequence should be same in the subsequence generated, then only it will be a valid subsequence. So you cannot be taking like this. For example, let's say 3 4 5 3 5 4. Now 5 and 4 order in this given sequence was different, and your subsequent that you are checking whether it's a subsequence or not, the order here is different, so it's not a valid one. So I hope it's clear to you what a subsequence is and what the elegance of a subsequence is. So you have to return the maximum elegance possible for a k length subsequence. K length subsequence. So you have to return this. Now you may think of a brute force way. What will be the brute force way? You may think we will generate all the subsequences, generate all subsequences and check their elegance. So what will be the number of subsequences possible? It will be nothing but if n is the size of the given sequence, what how many subsequences will be having this sequence will be having, it will be nothing but 2 raised to power n. Since for each element in the given sequence, you will be having two options, either to take this element in the subsequence that you are making or reject this element. So these two options will be repeated for n number of elements. So 2 raised to power n number of subsequences are possible. So, and what is the size of n here? It is of order 10 raised to power 5. So with 2 10 raised to power 5 is very much greater than 10 raised to power 8 operations allowed in 1 second. Those of you who are new to this concept, what is the concept? How the time complexity of a accepted solution varies according to the input size. Then I will be providing a link for article describing this concept. Right now, what I can tell you is, if the number of operations in your program are lesser than this 10 raised to power 8 operation, that you will solution will get accepted. Otherwise, if it's equal to or greater than this number of operations, then you may get a TLE, time limit exceeded, and your solution will not be accepted, or it will be rejected on the basis of time limit exceeded. So I will be optimizing this brute force approach. Let me quickly change the color. It needs to be optimized. So to optimize this brute force approach, what we can do is, let's say we sort the items, sort them according to descending values of profits they provide. And what we will be doing is, we will be selecting, let's say this is the resulting items array, 2D array after the sorting. This is the items 2D array after sorting. Okay. Now we will be picking k of these items, k items. Now let's say in a bag we are having k items which are providing maximum profit to us. But it's not necessary if they are providing maximum profit, their elegance is also maximum. Since elegance depend upon two factors, profit, total profit, plus number of distinct categories where. So this factor we will be checking for. What we will do is, if let's say you are initially having k items, and for each of the k items, let's say you are having some duplicates, or for some of the k items you are having duplicates of their categories. What I mean to say is, let's say you are allowed 3 items, and you take the items with, this is the profit, and this is the category of the item. Let's say you take these items, 3 items were allowed to you, and you take these. This is profit and this is category. Now you are having 2 items of same category, 2 items of same category. It may happen, it will, if currently these are representing the maximum profit that you will get. But what about this factor, square of the distinct categories? Now here you are having only two categories, if it's possible that if you replace one of these items which is uh, having duplicates of its categories, it means that its category is, it is not the only item of its category. Let's say you want to replace this item, this is not the only item of this category. In bag is nothing but a hypothetical construct here. So I have made so that have, you will be able to understand this problem in a clear way. Now let's say I decide to remove one item. Which item I should remove? I should be removing the one with least profit. And which item which is not the only item in the category, in the category of that item. So in category 4 there are two items, so we will be removing the one with the least profit. And what we will be doing is we will be adding another category item and checking if the current elegance exceeds then this modified elegance. And for all these replacements we will be checking the maximum elegance possible. Now it will be more clear to you in the coding part. Now let's quickly move to the coding part. So we have sorted items according to the descending order of profits. Sorted items according to descending order of profits. Okay. Now this set is to check the categories. Check the categories present in the bag currently. Bag is nothing but a hypothetical construct that we are imagining to understand the solution of the problem. So okay, this will be telling you the categories that are present in O of one time. It will tell you that these categories are either present on the bag or not. So these what this duplicate array is doing, this array is storing the duplicate category items whose profit is minimum. So let's say what will this duplicate array be containing in this example? Let me quickly move to a new slide so that you will be able to clearly see which example we are talking about here. 2 4 and 1 2. This represents the profit and this represents the category. So your categories set will be having categories 4 and 2. These are only two categories. And your duplicates array will be having the the item which is not the only item of its category and it is having the minimum profit that is it's providing. So what will be that item? That item will be nothing but this item 2 comma 4, this one. So it will be your category set, this will be your duplicates array. So what we will do is once we have collected all the key items in our bag, we will try to remove these kind of items and check if the updated elegance happens to be greater than the previous one, or among all the elegance is possible after doing updations, and we'll be returning maximum of such elegance possible. So here what we are doing is, if the current item is the is not the only item of its category present in bag, then we will push that item to the duplicates array, and that item will be of the minimum profit possible, because we have already sorted the items array in descending order, and this is to check if the bag is having less than a number of elements, or say items, a number of items. So you will be checking for that, and if it happens that you have encountered a new category and your bag is also full, what was the capacity of the bag? It was nothing but k. If the bag is full, capacity reached, which is k, and you have encountered a new category, check if there are any duplicates of the duplicate category items in the bag. If there are no duplicate category items in the bag, then you will return. You are already having the maximum elegance. You are already having maximum max elegance. And if that's not the case, what you will check is what will be the decrease in the profit if you decide to remove the item which is a duplicate item and which is having the least profit. And if you decide to remove that item from the duplicates array, where will that item be? There, that item will be at the very end of the duplicates array. And if we will check for the decrease in profit, now what will happen is the increase in the number of categories will be far more positive to the elegance of current subsequence than the decrease of the profit will be negative to the elegance of current subsequence. So you will be decreasing the profit, and what you will be doing is you will be increasing the number of categories, and for each of the subsequence possible, for each of the subsequence possible, you will be checking for the elegance. You will be checking for elegance, and at last you will be returning the maximum of such elegances. And so this wraps up the solution of the fourth problem. And what will the time complexity be? If let's say the size of the items array was n, then you were required to do sorting, and it will happen in of n log n time, and you are just iterating over the items array only once. So time complexity will be this much, and you have to store the categories So at most n categories will be present.